Um, Good morning. I'm Luigi Vigneri, a research scientist at IOTA Foundation. I'm here to present basically our technology and the work that our research department is doing and how we envision to include the verifiable delay function inside our technology. So to start, I would like to give a brief introduction on what are the main use cases and what is basically IOTA. Some of you may be familiar, some not. So basically, in the current cities and the current world, we have many devices connected, and each of them has to exchange information, exchange data, and the standard blockchain has been thought in order to send payments between different users, but many other data and information are available nowadays. So the main idea in IOTA is to enable the machine-to-machine economy in order to exchange this information through the devices that can be spread in cities, but also in houses. And we see that many electronic devices can communicate with each other in order to build this new ecosystem. So the main idea in IOTA is to replace the standard blockchain where each block approves the previous one, building this long chain. We are envisioning a system where we use a different data structure. So instead of having a chain, every transaction when it comes and arrives into the network can be attached to two previous transactions. This will build a directed acyclic graph, which we call the tangle. Why do we want to have this tangle? So I will give you here just two intuition on where we're gonna probably gain by having this different data structure, which is actually more complex but also more fluid and dynamic. So one idea is that scalability can be improved. So in a blockchain, basically, since one transaction goes after another, this creates a natural bottleneck where we envision that cannot reach a certain speed in terms of throughput. In the tangle, since we can attach all the transactions to anywhere in the network, this, in theory, guarantees that more activity can also guarantees more validation and to have more throughput. So obviously this is in principle because there needs to have additional validation check in the network in order to guarantee the security. But in our opinion, this is something that leads to potential further scalability. So this is one intuition. The second intuition I want to give is about fee. In a blockchain, you have a distinction between users and miners. And the miners build the backbone on the network, and they can charge users in order to let the transaction through the network. And in IOTA, this is not the case. We have overlapping between users and nodes and the miners, so we don't really have this notion of miners. And every use can generate networks, it can generate transactions, sorry. And this leads to the fact not to have fees inside the network. So basically, this scalability, zero-fee transaction can enable the Internet of Things of the future in order to exchange data between different nodes and enabling the microtransaction and consequently the machine-to-machine economy. So this is just a brief introduction on why IOTA. Now, we have a research department quite active, and it is composed by 16 researchers with really different background in mathematics, cryptography, computer science, physics. And our main goal right now is on the project called the Core Decide. The Core Decide is basically the current project where we want to remove a special helper node that help the current network in order to guarantee security. So Since this data structure, as you can see, is more complex than the standard blockchain. So in order to be guaranteed that this works without any security leakage, currently there is this additional helper nodes that makes the network stable. But we are actively working in order to get rid of it and guarantee fully decentralized network. In order to reach this goal, we are establishing many collaboration with academia. We have collaboration with Imperial College, with Cambridge, and we also have this informal exchange with a VDF alliance. And we have opened this $5 million grant for research related to coordicide. So everybody is interested in participating and collaborating, we can reach us out. What are the main project, the main sub-project and task that we're interested right now, and how the VDF come into the game? So the main building blocks right now I depicted here, these four. First of all, auto-peering. How nodes can discover each other and how they interact with each other. Then the consensus mechanism, so which transaction will be part of the network. And the networking layer in order to deal with the spam attacks and congestion control. All these building blocks, all these tasks must be carefully analyzed according to a reputation system. Our reputation system includes, consider what are the impact that a node will have in the network, so how this node will help the network, and take into account the token that is able to transfer, but also the activity and the help that goes in the network. So for instance, if it makes any malicious behavior, then it will be penalized. So VDF in this scenario can be connected to all of these blocks. In particular, through a distributed random number generator. I will say a few more words right now. And through an anti-spam mechanism for to deal with the networking layer. So why distributed random number generator? So basically, both the auto-peering and the consensus mechanism, which is called FPC, fast probabilistic consensus, needs a random number in order to be secure. For instance, the consensus mechanism is an iterative voting scheme where we have a random threshold that varies over time for each iteration in order to prevent an attacker for understanding this threshold and make a split on the network. So in order not to make the attacker have the possibility to make the network having a split, so we need a random threshold. So how to generate this random number? We basically want to build a committee, and this committee could potentially use a commit reveal scheme plus a VDF. The problem with this approach that we are currently working on is that we need this number quite frequently, and this random number should be generated every few seconds in order to have a short latency, a low latency in the consensus protocol. So right now, we are also investigating other solution, but this is a potential task to be explored more. The other task where we are interested for VDF is spam prevention. So we said we don't have differences between nodes and the miners, between users and miners, so everybody can contribute in a network. But since the consensus mechanism is not based purely on proof of work, every node could just issue a very large number of transactions by creating denial of service attack. So we want to constrain the throughput of each node in order to put a cap, a limit. Right now, this is done by having a fixed proof of work, but this introduces some discrepancy, because if I'm a node with specialized hardware, with FPGA, I can produce a very much larger amount of transaction than IoT devices, for instance. So here, the way we want to use VDF is slightly different than what was presented before. So I want to use VDF because it guarantees that there are a certain number of steps that can be done. So basically, the time needed to lock and to compute the VDF is more or less similar for all the nodes in the network. We also require to have a low verification time because I need fast verification. And we have drafted the first scheme based on Veselovsky VDF, which also uses obviously a modulus that should be shared and should be generated and shared by all nodes in the network. We are doing some investigation, some optimization in order to study the RSA key generation. Maybe Vassil can say a couple of words about this topic.
Thank you, Luigi. So within the IOTA Foundation, we do different research things about the VDF. So one of the stuff we do have some backgrounds, and we investigated various multi-exponentiation algorithms, but I'm going to talk briefly about our algorithm for generating large numbers, basically large prime numbers. So here is the key component, the RSA problem. This is RSA 768. How to factorize this number. We know that it takes huge efforts to compute the products, and this is the largest from the RSA challenge list factored number. The next we expect to see is RSA 1024, perhaps in the next 1-2 years. So basically the new idea is quite different what we are attempting to do. How about if we go, instead of investigating primes, to go to the other extreme, smooth numbers, numbers with very small prime factors. So the RSA challenge means, okay, you pick up 2 prime numbers. It's not immediately obvious, but yes, that we can do that quickly, and we can multiply them. Why don't we go to the other extreme, picking 2 smooth numbers with a very appropriate, careful definition of smoothness and add them? Is this a one-way function? Is this a one-way function? Well, that's not obvious. How can we define smoothness in order to secure this? If we bound the largest prime factor to log n to the power of k for k 2 plus epsilon, apparently, but this is just apparently, probabilistically, we can secure that every number can be represented as the sum of 2 smooth numbers. I had the privilege to discuss this conjecture about 20 years ago with the late Alfred van der Porten and also with Andrew Granfield. And Nigel Smart was doing PhD research on this field in the early 90s. And apparently the conjecture is correct. The question is, can we use it for something? For sure, it has one really big advantage in comparison to the factoring problem. It's much easier to produce 2 smooth numbers, and it's trivial to add them. But the question is this indeed a one-way function? If it is, how can we use it? So one potential use for this function is, let's say, in here. So that's the restriction we impose, 2 plus epsilon, to secure that every number can be represented. We don't have to go nearly as far as 2 plus epsilon. We may go to log n to the power of 1. And and the question, given n as sum of p plus q, it's not immediately obvious even how we can use the latest reduction to find p and q, because the exponents are non-negative numbers, and the latest reduction algorithm will return just integers, not exactly non-negative. For small sizes of smoothness, there are tricks to do, but if, let's say, the largest prime, we use the first, let's say, 1,000 primes, it's not obvious at all how to do that. So what we just try to propose here is, how about if we just generate a number which is the sum of 2 smooth numbers with the largest prime factor 19. So given n, is there a chance to find quickly p and q such that we know that the largest prime factor is 19? Of course, they have to be co-prime, but that's easy. You split the 2 set of small prime numbers evenly and then raise to the random exponents and add small exponents. So can we use this whole thing to to very quickly generate prime numbers not divisible by, let's say, the first 1,000 primes? So the point of the fast prime number generation is you produce a random number, you you do trial division up to the first, let's say, several hundred primes. And if the answer is no, you go to Rabin-Miller or Solvay-Strassen or any of the available computational number theory tests. Is there a chance to immediately produce a number very quickly, which is probably not divisible by the first, let's say, 500 primes? Well, apparently it is possible with the use of this approach, because you can, and especially in the distributed decentralized environment, you may have two nodes that are producing two smooth mutually prime numbers with a very appropriate definition of the smoothness. And then for the other nodes, they produce smooth numbers divisible by all these small primes with smaller exponents. And then once we add them, we quickly obtain a number which is not divisible by these small primes up to several hundred primes. Well, of course, we're investigating the details right now, but it seems like a really efficient, more efficient primality generation algorithm, and this is what we are trying to discuss, and I'll be very delighted to have discussion with you during the conference. Thank you.
Thank you.